What's up, everybody? We are going to kick things straight off with 2-3 day 2. We're going to be graphing parabolas yet again. Except this time, we are going to be using a form we've not yet seen. So, quick recap. A couple videos ago, we learned about vertex form. Vertex form, also graphing parabolas with transformations, looks like y equals a times x minus h squared plus k. And here we can we can see the vertex that's present in this equation. So we can see that in there. It's been shifted over, shifted up, and then remember a changes the shape. So that one, graphing those, we were kind of shifting things around. Then in 2-3 day 1, we learned standard form. Standard form. Standard form is y equals ax squared plus bx plus c. Now remember, parabolas can be represented in vertex form. They can also be represented in standard form. And to graph standard form, we'll go over that process here in just a minute. To graph standard form, we first found the axis of symmetry, which was negative b over 2a, and then we took that value and substituted in for x to find the y-coordinate of the vertex, and you're going to see an example of that in just a minute. This a that's present in vertex form and standard form behaves the same way in both forms. It controls the shape of the parabola. The b here kind of controls the axis of symmetry, or is part of that, contributes to the shifting of the left and to the right. And then c is always our y-intercept, which is pretty exciting. And today we're going to be looking at another form, and so we're going to be learning another technique. So we're going to be looking at factored form of parabolas. And when a parabola is factored, what it allows us to see is where the parabola crosses the x-axis very easily. And that's useful information too, as we'll see in the next couple examples. So vertex form allows us to see the vertex in the equation. Standard form looks like y equals ax squared plus bx plus c. And vertex form is going to look something like y equals, k times, and then you'll have a bunch of like linear binomials. It might be like x plus 3 or x minus 5. Now this is a really general or this is just rather a random example. They're not all going to look exactly like this. You might run into some that have, that look like 2x or 4x. So if I were to really write it general, it would be like k times ax plus b times cx. Cx plus d. So that's a little bit confusing, but they're going to look like this. And for the most part, the first ones are going to be pretty simple, so there's no need to worry. Before we get into the factored form technique, let's do a quick reminder of how we graph with standard form, as promised. So I'll start at the top. First things first, let's identify a, b, and c. A, remember, is always the coefficient of the squared term, b is always the coefficient of the x of the first term, and c is always our y-intercept. So in this case, a is 1, b is negative 4, c is 0. So we can go ahead and find our axis of symmetry. X equals negative b over 2a, so x equals negative 4 over 2 times 1, which is 4 over 2, which is 2. So our axis of symmetry is going to be good, looking good. Now remember, to find the axis of symmetry, we take this value and we are going to plug it into the equation. Sorry, to find the vertex, we're going to take the axis of symmetry value and we're going to plug that into the equation for x. So here we end up with y equals 2 squared minus 4 times 2, which is y equals 4 minus 8. So y equals negative 4. So our vertex is 2 comma negative 4. So let's go to 2 down to negative 4. So we know our vertex is on the line, right? It's got to be on this axis of symmetry. Okay, but now we need some more points from our graph. Well, the easy one to get, if you wanted to do a real basic graph, the easy one is the y-intercept is always c, and c is 0, so we know that this crosses right about here. Now, really, you need one more point, and we can reflect that point once we have that. We need one more point from here, but the way that I would get those points is probably by using the shape. We know that a equals 1, which means this has the same shape as the parent function. Looks just like the parent function. The parent function is over 1. So 1 squared is 1, 2 squared is 4, 3 squared is 2. That's too far. You're going up to right, her. Right? 3, yep, this looks right. We got to reflect this point as well. And then we get our shape of our parabola. Beautiful. All right, so as a warm-up, you guys go ahead and try this next one. Here. Give it a shot. I'm going to go over here in just a minute. All right, here we go. A is equal to -1, B is equal to 2, C is equal to 3. So that looks like our axis of symmetry should be x equals negative b over 2a, which is -2 over 2 times -1, which is -2 over -2, which is 1. Oh, yeah. Sweet. Looking good. All right. Now, our vertex is somewhere on this line. We got to figure out where, so we're going to plug in +1. It'll be y equals -1 squared plus 2 times 1 plus 3, which is y equals 1 squared is -1 plus 2 plus 3, which is -1 plus 5, which is 4. So our vertex here is 1, comma. Okay. Similarly, C is our y-intercept. So it's got a cross right there. We can reflect that point. And I know that A is my parent function. Or A is -1, which means this is the reflected parent function. Reflected parent function, which means I go over 1, down 1, over 2, down 4, reflect over 3, down 2, 4, 6, 8. Oh, that again. Cool, so hope you got that right as we're moving forward, because knowing the shape is important. Now these next ones, I'm going to go into quite a bit of detail about how to graph them, but first I want us to take a look at one quick thing. What do you notice about the location of the x-intercepts and the axis of symmetry? Right? Parabolas are symmetric. Since they are symmetric, we know that they're crossing at the same spot relative to that axis of symmetry. Or rather, if I find one x-intercept and I know the axis of symmetry, I can reflect it over to find the other, right? They're symmetric. In other words, the axis of symmetry is halfway between the two x-intercepts, right? It's exactly halfway between. So if you can see here, we're at 0 and 4. Our axis of symmetry that's a length of 4, so you go 2 away from either one to find the axis of symmetry. Now, we're going to be using that information shortly to know how to find the vertex, which is kind of exciting. So let's go ahead and see one of those examples. Actually, but first, we need to make sure we remember what it means to be an x-intercept, what it means to be a y-intercept. Remember, x-intercepts are always on the x-axis, and every point on the x-axis, like this point, this point, this point, this point, this is the point 1, 0, this is the point -2, 0. Every single point on the x-axis has the y value 0. So what we can do is, given any equation or any function, we can plug in the y value 0. To find the x-intercepts, we can plug in y equals 0. So plug the y value of 0 into the function and then solve or evaluate to find the x-intercepts. Okay, so and remember, what's that going to look like here? So to find the x-intercept, plug in y equals 0, and we can, a parabola might look like this. You might have, two x-intercepts like that. A parabola might look like this. It could be facing up or down, opening up, opening down. It could not cross at all. And it is quite possible for there to be only one x-intercept. It looks like this. So cool. So if the vertex is on the x-axis, then you have one x-intercept. If it crosses 2 times like this, then you'll have 2 x-intercepts, and if it's shifted up and doesn't cross, you'll have no x-intercepts. So it's possible to have 1, 2, or 0. Okay, how do we find the y-intercepts? Remember, the y-intercept is going to look like this. So although this green parabola has no x-intercepts, it does have a y-intercept. Okay, so to find the y-intercepts, it's kind of a similar comment. Every point on the y-axis has the x value 0, right? 0, -1. Every point on the y-axis has the x value of 0. So to find the y-intercepts, you plug in x equals 0. Cool. Nice little reminder. How many possible y-intercepts can you have for a quadratic function? Well, quadratics domain is from -infinity to infinity, so it has to cross somewhere. Quadratic's going to have one x-intercept, one y-intercept. Here we go. Find the x and y-intercepts and the vertex for the following quadratic functions. Use the sketch of the graph to sketch the graph of your. These to sketch the graph of your quadratic function. So first things first. I'm going to go through in blue. We're going to find our x-intercepts, and to remember, to find our x-intercepts, we're plugging in y equals 0. To find our x-intercepts, we're plugging in y equals 0. So step 1, find your x-intercepts. So you go, remember this f of x is really just a big y. You can think about that as y. So this is really 0 equals x minus 1 times x plus 3, like so. So how is it possible for this this is a product. How is it possible for this product to be 0? Well, there's this thing called the zero product property that says if you're multiplying two things and the product is 0, the only way that is possible is, or rather, how can we make this equation true? The equation is true if a equals 0 and or b equals 0. So a b equals 0 is a solution, and a equals 0 is a solution to this equation. So when we're solving this equation, what values of x make this true? Well, the value of x that makes this true, one of them is the one that makes x minus 1 equal to 0, and that is the value x equals 1. So x equals 1 is the solution, because 1 minus 1 is 0, and 0 times whatever that'll be, 3, is equal to 0. So 1 makes the equation true. Here's our product. The other number that will make it true will be if this thing is equal to 0, because then 0 times that will be 0, and you'll get x plus 3 equals 0. So x equals -3 is a solution as well. So we know that our parabola that has, these are our two x-intercepts. We know that our parabola has two x-intercepts. It crosses at 1, and it crosses at -3, which is right here. Our parabola crosses here and here. That is enough information for us to deduce that we can find our axis of symmetry. Our axis of symmetry in the previous examples was always in between, halfway in between our two x-intercepts. So I'm going to go back here. This means our axis of symmetry is the line x equals, what's halfway between -3 and 1? Well, it's 4 long, so you go 2 this way, which is x equals -1. X equals -1 is our axis of symmetry. Now I know that the vertex has to be on that axis of symmetry. So how can I find the y coordinate of the vertex? So we can now, in red, let's find the vertex. The next step is going to be to find the vertex, which means I can take my -1 and I can plug this in. That's going to be y equals -1 minus 1 times, times -1 plus 3. So here we get -2 times 2, which is y equals -4. Okay, so y equals -4 is the y coordinate of our vertex. It looks like -1, -4. So we're going down like this. Beautiful. Cool. So we found our vertex. Great. Not quite done yet, because it says find the x and y intercepts, right? So the y-intercept we'll do next. Remember, the y-intercept is always where x equals 0. This is the easiest one to do. So you just go y equals 0 minus 1 times 0 plus 3, which will give you y equals -1 times 3, which is -3. So our y-intercept is -3, which means it crosses right there. We can reflect that point. Now that, you should be able to recognize that that has an a value of 1. I go over 1 from my vertex, up 1. So this is the same shape as the parent function. So that means we can kind of fill in the rest of our points based on that pattern. Over 2 up 4, over 3 up 9. Cool. And then there we have our parabola. So I started with the x-intercepts. I used that to find the axis of symmetry. And I used that to find the vertex. And then I used x equals 0 to find my y-intercept. And that's pretty exciting. Now, technically, you could stop at the vertex, but it's nice to find that y-intercept by the method that was taught. Well, okay. Now, I told you that these can be represented in different ways. So I'm going to do a little aside right here. You don't have to write this down. Remember, our function is y equals x minus 1 times x plus 3. If we were to multiply this out, or expand, we would get y equals x squared plus 3x minus 1x, -1 times 3, minus 3, which gives us y equals x squared plus 2x minus 3. So there's our y-intercept of -3. As we can see, we can kind of check our work. And it has a shape of 1. Now, if you were really struggling to graph this, you could multiply it out and then just use the method from the previous day. That would work. And you do, negative b over 2a to get -2 over 2 times 1, which give you your axis of symmetry of -1, and then you're off to the races. But this method that ignoring the black here, this method is can be very quick as well. It's really easy to look and see, hey, what makes this 0, 1? What makes this 0, -3? Boom, boom. Half axis of symmetry is halfway between there. What's my y-intercept? What's -1 times 3? Oh, it's -3, right? You can plug this in and do this very, very quickly, mentally, and get your quadratic graphed. So factored form has its benefits. It can be done really quickly. You guys are going to try this next one. I am going to try and get you started a little bit. I want to talk about one thing really quickly. So let's do x-intercepts. We're going to start off the exact same way we did. X-intercept is where y equals 0, so you plug in 0 for y and you'll get 0 equals 2 times x plus 1 times x plus 3. Now, forget about that for just a second. If I say 2x equals 0, we can divide both sides by 2 to get x equals 0, right? The same thing happens here, right? I can divide, I'm going to change ink colors if you don't mind. I can divide, oh, that is ghastly. Oh, I wish I had orange. I can divide both sides by 2. What we do to one side, we do to the other. All right, and then we end up with 0 divided by 2 is 0, and then x plus 1 times x plus 3 is the equation we have to solve. And we can use that zero product property, or the a times b equals 0 thing, to figure out what our two numbers are that make this true. So I'm going to turn you guys loose. I want you to start with the x-intercept, get the axis of symmetry, get the vertex, get the y-intercept, and put your graph together. Be careful. This one's a little bit tricky because the 2 out here can mess you up a little bit. All right. You can unpause the video when you think you want to check your answer. All right, here we go. 2 solutions. The 2 values that make this equation true. The only way it's true is if this goes to, when this goes to 0 and when this goes to 0. So that is, set this equal to 0 and solve. So x equals -1 is one of them. And x plus 3 equals 0. X equals -3. Okay, those are our 2 x-intercepts, which means my axis of symmetry is going to be x equals halfway between those 2 values, which is x equals -2. All right, now let's go ahead and find the vertex. The vertex, somewhere on that line, so we plug -2 into our equation, which will give us 2 times -2 plus 1 times -2 plus 3, which is y equals 2 times -1 times 1, which is y equals -2. So our vertex is -2, -2. Okay. Awesome. Lastly, our y-intercept. Let's get down here. Let's get down to business. The y-intercept is where x equals 0. So plug in 0 for that and for x, and you'll get y equals 2 times 0 plus 1 times 0 plus 3. Y equals 2 times 1 plus 3, which is y equals 6. So our vertex is, our y-intercept is 0, 6. Now let's see if that makes sense. If I were to multiply these two things out, we would get, it would be x squared plus, I think, like plus 4x plus 3. And then we distribute the 2 to everything, and then our a value would be 2. So this looks like it's been stretched out. Normally we'd go over 1 up 1 from the vertex if it has a parent junction, but we're going up twice as much. Normally we go over 2 up 4 because 2 squared is 4, but we're going up 8, so it jives. This makes sense with what we've done in the past. I like this method. I think it's a lot of fun. That's horrible. Alright, you guys are getting the race car sound effects upstairs. Okay, there's our parabola in all its glory. Yay! Okay, we're going to crank out some word problems. So stay tuned. Let's get started. A person is standing close to the edge of a 150-foot building, throws a baseball vertically upward. The function s of t equals -16t squared plus 64t plus 160 models the height of the ball above the ground in feet, t seconds after it's thrown. When does the ball reach its maximum height? What is the maximum height? So this is kind of a review of what we've done in the past. So it's going to look like this. Okay, so this person's standing. I'm going to put the tall building right on the y-axis. So let's just make sure we understand the picture. There's like a dude standing at on a tall building, and he's chucking a ball like this, and it's going to fall down like so. This ball plummeting towards the earth. We're wanting to know what the maximum height is, and we're wanting to know when the ball reaches its maximum height. Now this is the path of the ball that I'm drawing here, but you could also, there's going to be, a time associated with this ball as well, and its position. So this equation models time, but you can see that it's going to be a quadratic as well. It makes sense for it to be one. So how do we find when does the ball reach its maximum height? Because this horizontal axis is t, right? Well, sure. We'll call this s of t up here. Our height. When does it reach that max height? When means we need to find our axis of symmetry. That's going to be t equals negative b over 2a. So if we run up to our equation, b is 64, so it'll be negative 64 over 2 times negative, 2 times negative 16, negative 64 over negative 32, which is value of 2. So 2 seconds. 2 seconds after the throw is when it reaches its maximum height. I guess that's pretty believable. 2-second throw. Pretty believable. Okay, so at 2 seconds, this is the time. This is when it reaches max height. And to find that max height, all we do is plug that in to our equation. We need to find, okay, so to find the max height, all we do is plug in 2 for t, so it'll be s of 2, which is negative 16 times 2 squared plus 64 times 2 plus 160. All right, so that's going to be negative 16 times 4 plus 64 times 2 plus 160, which is negative 64 plus 128 plus 160. I'll add the first two there. That's 64 plus 160, which is 220, right? 224 feet high. So the max height is 224 feet because it's got to happen at that time of 2 seconds. Yeah, let's take a look at this next one. I love this question. You have a 600 feet of fencing to enclose a rectangular plot that borders a river. If you do not fence the side along the river, find the length and width of the plot that will maximize your area. What's the largest area that can be enclosed? Oh, this is so fun. I'm going to draw a little picture. All right, let's say you live on a let's say you live on a riverbank. You're like ultra hippie. You're making one of those YouTube channels where you sustainably live for 12 years and film it and get a sick beard. And you want to fence. You're not, basically what I'm saying is you're not restricted on the amount of land you can use here, right? You got 600 feet of fencing, and you're going to construct a fence next to the river. Now, you don't want, it's a 3-sided shape, right? This is not, the river is one side, that you don't need to worry about, basically, or maybe there's a cliff or something there. So we're constructing a fence that's going to look like this. And we know it's a rectangle, so we know that these two things are the same. And that should kind of make sense. So there's a bunch of different ways that you could do this. Now, you could draw a couple little examples to try and think about this. Maybe the river looks like this. Sounds pretty dramatic up there, Oscar. Okay. Now, there's a lot of things that you could do that would be kind of crazy. Like you could make this section 1 foot long, this section 1 foot long, and that would mean since you had 600 feet of fencing, this would be 598 feet long, which would give you a 598. Yeah, it seems right. This would give you an area of 598 feet squared if you did that, and that's not very big, right? It's just going to be this really long rectangle. You're not going to be able to fit a bunch of potatoes and carrots and all the stuff that you want to grow in there. Similarly, you could go like this. You could make one side of the fence equal to, I don't know, let's say 100. You'd make this 100, which means this would be 100, which means this would be 400 feet. And 100 times 400 is a 4 with 1, 2, 3, 4 zeros. That would be 40,000 square feet. So what we need to do is we need to find a general equation that models the area of our fenced-in garden. Now, this is going to hold a heck of a lot more potatoes than the first option, right? We need to find one that models the area of this. So I know the area of a rectangle is length times width. So if I can find the length of the width of the rectangle, we're golden. Now, how do we started with these two being the same? So I said this is 1, this is 1, and then we figured out what that is, right? So here we go. The height here is x. We know that these are the same. That's what we're starting with. And this length is always based off of what we chose for this. So I said, well, this is x, this is x, and then we took that and subtracted it from 600, which was the total. So the length here is just going to be, we used x here, we used x here. This length is going to be 600 minus 2x. Okay? And since the area of a rectangle is equal to length times width, then the area of our rectangle here is going to be, length is, let's say, whatever, length times width, we'll say x times 600 minus 2x, which gives us 600x minus 2x squared. So we have a parabola here, which is exciting, okay? This is a quadratic function. The area of our fencing, when we change x, can be modeled by a quadratic, which means there's a graph associated with that, right? When we make the area 1, right, you know, it's going to look something like this. It's upside down. A is equal to -2. So that means that there's going to be a maximum area that we can use. And that means there is an x value that maximizes that area. And we need to find that. And this is actually pretty easy. All we have to do is find our axis of symmetry here. Our axis of symmetry is x equals, again, -b over 2a, which is, in this case, b is 600. So it'll be -600 divided by 2 times -2, which is -600 divided by -4, which is 300. It's 150. All right. All right, so we know our area is, the x value, rather the length or whatever that is, this x dimension, x is 150, is the x value that maximizes the area and maximizes the amount of vegetables that we can grow in that space. And again, the units there for x are in, are in feet. Okay, so now we need to find the area, the max area that's possible. So to find the max area, we know the area equation. It is this area equals 600x minus 2x squared. So I'm going to do area equals 600 times 150 minus 2 times 150 squared. This is a lot of math. I'm going to pause the video and then show it. Alright, so let's take a look here. So I plugged in 150. We did 600 times 150 is 90,000. I did 150 squared is 22,500 times 2 is 45,000, which means the maximum area that is achievable is 45,000 square feet. Pretty exciting. Cool. I dig that. All right, so we weren't too far off with our guess at 100. Looked pretty good, turns out. So 150 is gonna do it. Sweet deal. This is a similar question. It's our last one. If you want to try this on your own, I would encourage it. It's not too bad. And so what it's saying is rain gutters are made from long sheets of aluminum. They're bent up. You can go to places in town and have them made. The aluminum that we're turning is 20 inches wide, and you're turning them up at right angles to form your gutters. So basically, what I want you to imagine happening here is we're making our rain gutter. We have a long sheet of aluminum like this, and we know that it's 20 inches long. Okay, it's 20 inches long, and basically, we're going to take these little points right here. We're going to fold them together, and we're going to fold up our gutter. Whoops. We're going to fold it up. Get out of here. We're going to fold it up like so. So the gutter is going to get folded up, and when it's hanging on our house, on the edge of our house, it's going to look like this. Okay? And basically, you could do a lot of things with your gutter, right? This is a very similar question. You're trying to decide how to fold your gutter. You could make your gutter like this and make it really, really tall, but it's not going to hold a ton of water. You could also make your gutter, extremely wide like this, but also wouldn't hold a ton of water. So the question here is asking us, it's asking us, determine the depth of the gutter that will maximize the cross-sectional area. If we maximize the area of our gutter, then we're maximizing the amount of water that it can hold and flow down. So let's go ahead and do that math. We know that the whole thing is 20, and this is a very similar problem. We know the whole thing is 20 long. The question, the thing that's concerning us, is where to make our folds. So that's what we're going to call x. Whoops. Go here. So this is x. This is x. Those are going to be the same because we're kind of folding them up into a rectangle. And if that's x and this x, similarly, what would this have to be? Well, let's think of a couple examples, right? If this was 1 and this is 1, this would be 18, right? You add these up and subtract them from 20. So this is going to be 20 minus 2x. Okay, so to find the cross-sectional area of our gutter here, it's just a rectangle. It's going to be length times width again. The length will say x, the width will say 20 minus 2x. Fun, fun, fun. So our area is equal to 20x minus 2x squared. Yeah, looks good. So we have a parabola. Again, it's opening downward like so. Has a y-intercept of 0, right? It's opening downward. We need to figure out what our max is. Yeah, this looks good. Pretty exciting. There's a couple ways you can do this. You can do this with the axis of symmetry is what I'll do. You can also factor this and use the factored form to solve as well, but we'll just forge ahead with the axis of symmetry. So that's x equals negative b over 2a, right? That's where my maximum is going to occur. It's always at that point, which is negative 20 over 2 times negative 2, which is a negative 20 over negative 4, which is 5. So when x is 5 inches, we have maximized our gutter. And so, you can do it you can find this by plugging it into the equation. You can also draw a little picture, right? If this is 5, this is 5, which means you have a total of 10 remaining. So the maximum cross-sectional area is 50 inches squared. Or you can get that same value by taking this, plugging it in for x, which is, so this is the point here, 5 comma d. You can see that. 20 times 5 minus 2 times 5 squared, which is 100 minus 2 times 25, which is 100 minus 50, which is 50. Alright, hope this is a cool video. Those are some fun word questions. Thanks for watching. I really appreciate you. See you next time. Thanks for watching the Mathnasium. Like and subscribe. Blah, 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 blah.